World. My name's David Watson. I'm one of the technical directors at AKT II, and I'm going to be joined this evening by my colleague Michael Hynd, who's also technical director here at AKT II. We're going to give you a whistle-stop tour through the structural design of the building HYLO, which we can actually see from our offices where we're sat now. We see it every day. But before we do that, I thought I'd just give a very brief introduction to who we are at AKT and the AKT II team. So when it comes to any project that we work on, it is a team effort. And really, when we're talking about an AKT II design, it is everybody. And for those that are good at Where's Wally, you can spot myself and Michael down at the bottom here. But really, as I say, it is a team effort. And this project is, from the structural side, a team effort across all of those that have worked on the project, past and present at the company. AKT II, we're a firm of consulting structural and civil engineers. We have geotechnical and envelopes teams and a bioclimatic team also. We work in all sorts of regions around the world on all sorts of buildings. We're very culturally diverse as a practice. We bring all of that experience to bear on our projects, and we number just over 320, principally in our London office, but we also have offices in Manchester, in Cambridge, and in Denmark. So HYLO is a reuse scheme. It is a reimagining of what we can do with an existing medium-rise tower building. But it represents a culmination, really, of a path that started over 25 years ago now, with reuse projects, early reuse projects such as the Angel Building, and have recently found all of that experience being brought to bear on projects such as 100 Liverpool Street, recently Sterling Prize nominated, and the project that we're talking about this evening, HYLO. So you can see that this really is a journey that has happened over the past 25 years, increasing scale and increasing ambition with respect to reuse over that period. So I'm going to pass across to Michael. Before we do that, I'm just going to give a little bit of an introduction. So I am one of the technical directors here. My background is in reuse, principally, and I'm going to be talking principally this evening about the foundation reuse. Michael will be picking up the scheme as a whole. And so I'm going to pass across to Mike.
Thanks very much, David. So just to sort of give a sort of high-level overview, this is obviously a project that we're very proud of. We're very pleased to have won or to be joint winners of the Supreme Award from last year from the institution. And the aim of this lecture is really just to give an insight into the design process that we undertook, hopefully also to promote the inherent benefits of retrofit as opposed to wholesale demolition and rebuild. So just to start by giving a little bit of the background. So as David said, this was a transformation of an existing mid-century building known as Finsbury Tower, which was located in central London, into a modern high-rise development. In terms of the project team, that consisted of our client, the developer CIT, the architect Horden Cherry Lee, and Mace as a principal contractor, who were also aided by Jay Coffees, who did the enabling works. Our involvement in this project dates from back in 2015 when CIT first purchased the site up to its completion last year. So just to give a little bit about the site context, so it lies within the borough of Islington, a street called Bunhill Row, and it's really at the intersection between the historic city of London and the sort of emerging technology hub around Old Street, also known as Silicon Roundabout. The existing tower was constructed in the 1960s. It was 16 stories in height and just under 60 meters, with a smaller surrounding podium structure, which varied between 1 and 4 floors in height. And it's probably safe to say that this urban context was paramount during the sort of early planning stages. And from this image here, you can see a little bit of the surrounding context. So there's 2 designated conservation areas nearby. The building overlooks the Honourable Artillery Company's historic Finsbury Barracks, and also sort of other low-rise conservation areas. It serves a little bit of a bridge between sort of mid-rise sort of Islington surrounding townscape, some of the new high-rise developments around Old Street Roundabout, and the established sort of financial hub of the city. You can also see there that you've got Barbican Tower very close by, and if you look very closely, you can just about pick out our Office White Colour Factory, which is just down the road. In terms of the existing building, so it was designed by the renowned brutalist architect Richard Seifert, and was built between the years of 1966 and 67. And as you can probably see from some of the images here, it was rather unsympathetically refurbished in the early 90s. And the sort of rain screen facade that was installed was starting to fail in 2015. So leaking, air, water, and heat due to the aging fabric. On some of the initial site visits, there was areas of damp and visible damage present to some floors for the internal partitions and ceilings, and the building was largely unoccupied when CIT purchased it in 2015. So in terms of the client brief, so obviously obtaining a sort of elegant architectural design, was imperative to the client. But in order for this building to be sort of truly sustainable and to fit into its surroundings, the form needed to respond to the urban and historical context that we talked about just a minute ago. It also needed to be enduring, both in terms of its appearance and in terms of the physical enhancement to its design life and future adaptability and use. The brief was that the building should incorporate a range of uses and also enhance local amenities. It was achieved via provision of things like new affordable housing within the site footprint, new public realm spaces, podium-top terraces and gardens, and a range of shops, cafes, restaurants. The idea being to help regenerate and sort of reactivate the local area. There's also a range of flexible office typologies that CIT were looking for, including affordable workspaces. It is, however, fair to say that the primary driver, at least from sort of economic perspective, was to actually maximise the increase in net lettable area on the site, whilst reusing as much of the existing frame as possible. So just going to briefly touch on the final form of the building. So effectively, we've added 13 additional steel frame floors to the existing 16-storey tower, which in terms of percentages is approximately 70% increase in the overall height of the building. All of this was obtained while reusing the entirety of the existing basement box, the foundations, and as much of the existing frame as possible. Through I'd say a granular analysis of the existing structure, we've been able to target most of the new loads and strategically direct them into areas that had spare capacity. This allowed for minimal intervention with respect to column strengthening and a minimum amount of additional piles. Altogether, the scheme effectively doubles the site's leasable area up to just under 26,000 square metres. Whilst also saving around 35% in the upfront carbon cost when compared to an equivalent new build construction. So just sort of zooming into some of the typical floor plates and try and explain a little bit more. So these images here show the sort of extent of the typical retained and extension floors. It's worth noting from the outset that the extent of the tower retention was primarily driven by the existing cores. So these didn't provide sufficient capacity in terms of either lateral stability or plan area for the new lifts to serve the extended floor plates, and so they had to be replaced. So that was one thing that dictated the maximum amount of retention and cut lines. What this did allow us to do, however, was to place the new cores eccentrically, as you can see on the left-hand side of the plan there, and that also helped to open up what was a previously fairly cramped office floor plate and also providing the required enhanced stability. Also, in order to maintain a consistent perimeter slab edge, because when we were doing the sort of cut and carve, there was a degree of variation in the setting out of the perimeter slab from the 1960s construction. We added a steel extension plate around the perimeter that also gave a consistent support for the new facade. On the extension floors, we've obviously extended the floors upwards using lightweight steel framing, and this also allowed for increased column-free spans, which acted to minimize the weight on the existing columns and therefore foundations. These increased spans were actually more efficient for steel design, so we're talking about approximately 12-meter spans for secondaries. So that helped to reduce the overall number of columns that required strengthening by targeting the loads to areas where there was spare redundancy. It's fair to say there was also some provision made for future flexibility and adaptability with regards to future soft spots and an agreed level of redundancy to the new structure. So just to touch briefly again on the existing building. So as previously mentioned, it was a 16-story RC frame, typically on a 7.5 by 6 meter grid with a 305mm thick slab. The stability was provided via the two RC cores, which you can see on the right-hand side of the image there. Obviously, as you can see, one of them is purely stair, the other one is a combined stair and lift core. And I think it's probably easy to see with the additional floors that plan area would not be sufficient to achieve suitable lifting requirements. Sorry, David, you can flip back to that. Sorry. So basically, again, by placing those cores eccentrically, we were also able to gain a little bit in terms of plan area. So the red highlighted area there is the extent of demolition. The green is the sort of gain that we've had on the floor plate within the tower floors. So I guess the main question is, how do we achieve this degree of intervention and expansion on the existing building? Well, the first and really the most important step was to really invest in learning as much as possible about the existing structure. So we spent a large amount of time at the start of the project, trawling through archives, interrogating all the available record drawings. We tracked down the original structural engineers and obtained copies of the general arrangement and a limited selection of RC detailing drawings from them. Given this brief to obviously maximise the extension, it was also therefore necessary to supplement this information with additional site investigations and fabric surveys, just to verify that the information we had was effectively the as-built. And all of this was then used to undertake forensic back analysis of the existing frame in order to extract the maximum residual capacity from the 1960s design.
I think it's worth highlighting at this point just how important this initial stage is and how much effort needs to go into it. You really have to live the building through the information that's available and look for all of those opportunities, all of those potential rationalizations, inherent capacities that might be hidden, not so obvious within the existing building. It's a really, really important stage, and I think it points to an important lesson for the future, that one of the best things that we can do as engineers is keep these records for future generations of engineers to use.
So also sort of briefly touching on the existing foundations. So we obtained existing drawings and pile schedules. So we knew from those that the building was founded on a series of large diameter under-ream piles, up to about 1.8 meters diameter and 3.8 at the base of the under-ream. And as you can see, we've got single under-reamed piles under columns, and then we've got a sort of group pile cap under the stability cores. So I think it was approximately 1.9 meters deep pile cap that supported the cores. We also found from interrogating the record drawings that the original design imposed floor loading was up to between 8 and 9 kilopascals in some area across the building, which is obviously substantially higher than modern office loading of 2.5. It's believed that a condition for or planning condition potentially for the existing building was that it was designed to accommodate floor loadings in the eventuality that part of the building was taken up as a printing press. The reason for that is that the site historically housed the De La Rue Printworks, who were, I think, the largest printer of sort of banknotes. That building was destroyed in World War II, and we think potentially that the reason for this sort of large imposed loads was that as part of the redevelopment of the site, there was a condition that, they had to make future allowance for them to move back in. In the eventuality, it was never occupied as a printing press, but we used this, additional redundancy in order to sort of justify load, the increased loads on the foundations, and we look to exploit that as much as possible with the reuse.
So these initial searches put us in a good position to feel confident that we're able to back analyze a certain amount of the capacity of the structure also. But they are it is record information at the end of the day, and so we do need to still validate it, which then led us on to a series of investigations. So, Mike, do you want to run us through that?
Sure. So, during the early stages of the project, we developed a range of additional investigation briefs in order to verify, as David said, the record information. So these ranged from ferroscan surveys of existing slabs and columns, representative samples of concrete cores, which were taken for strength and chemical testing, geotechnical investigations, so boreholes obviously for soil design parameters. These were enhanced by pressure meter testing in one of the bores, and we also did, as we'll come on to later, a degree of testing of the existing underream piles. So, given the sort of fairly tight construction program that the project we're under, we phased those investigations into sort of two stages. So early on, because as I said at the start, the building was only sort of partially occupied, there was areas of floor plates that were unused that we could take out, the raised floors early on, and that allowed us to do some ferroscan surveys to try and verify compared to the record RC detailing drawings. So we did this over a representative sample of the slabs, columns, and walls. This was undertaken shortly after the purchase of the site. You can see on the right-hand side there's an image much later on in the process where we scabbled the faces of some of the columns that were not being reused, and we were able to verify by physical measurement bar diameters, cover, etc. The second phase, obviously, once we had vacant possession, we were able to undertake core samples of the slabs and columns. That was undertaken to determine, obviously, concrete compressive strength, chemical testing done to check for any issues such as carbonation, the presence of sulfite or chlorides within the concrete mix. And as we just mentioned previously, in the areas that were going to be demolished and not retained, we undertook an extensive survey measuring the existing rebar, spacing, cover. Again, all of this further verifying the information from the record drawings. It's worth noting that from the core samples taken, the compressive strength of concrete was derived to be about 10% greater than that stated in the archive drawings. Again, all these things we've taken the benefit of in terms of the sort of detailed back analysis.
And we thought it was worthwhile just explaining a little bit about what we did in terms of the pile verification. So we had a series of underreams. One of the very important investigations was once we'd determined the piles that were going to be most heavily loaded, we wanted wanted to check that those underreams, the bells, had been formed as documented. And so we actually just sunk a small diameter borehole, essentially, just adjacent to the shaft, with the intent to hit that underream. And in doing so, we can physically confirm the size. We do that over a representative sample with a focus on those areas that are more heavily loaded, and we get comfort that for the purpose of the foundation design, we validated the record information. We also had the opportunity, while we did that, to look at condition. We could take samples while the head of a number of those piles was exposed, knowing that they were going to be cut down in the future. And so we could complete the picture not only of validation, but also looking at the condition of the piles. And that then led us into the consideration of the foundation reuse. So Mike described the really intense initial phase where we look at all of the record information, we build a picture of the structure, and then we look at what we want to add to the structure. And we're trying to identify where the fuse in the system is. Where is the point in the structure that is going to limit our ability to extend the building? And what we want to do as part of that is to really look closely at the foundation. There are options available to us, and we'll see later on in the presentation, in the superstructure when it comes to strengthening. When it comes to the foundation, we can often be more constrained. So we put a particular focus there early on. And the brief, as we worked through the different options on the foundation, was clearly to maximize reuse as far as possible, to maximize what was already in the ground. There's a lot of concrete volume in the foundation. Let's make sure that we're utilizing it in the best way, and ideally even pushing it beyond what it was initially intended for. And we mentioned earlier that there were areas of redundancy with respect to higher than required design loads in the structure. So let's make sure that we build on that. We're not wasting material in situ, therefore. It was very, very clear that the ambition to increase the height of the building was going to put significant increased demand on the stability system. So we needed to support those new cores. There were going to be heavy elements. That almost certainly would mean that we would need to make some interventions. And we also then needed to look at limiting the settlement of those retained elements and the new elements. Being constructed at different times, having experienced different degrees of consolidation in the London clay, this was going to lead us down the route of having to adopt a performance-based design and really look specifically at prediction of settlement through the whole sequence from the original construction through to our proposal. And when we say performance-based design, what we mean by this is that it really is taking it beyond just a simple deemed to satisfy factor of safety, and really looking at how to make use of the predictions that we can now make with respect to settlement, with respect to the transfer of load into the ground. And this opens up a whole range of more complex hybrid foundations. And so quite quickly, we identified here that we would be needing to supplement what was there already. They were underreams. There wasn't really going to be the opportunity for us to supplement them with similar piles going forward, and so we looked for what would be available to us. And we settled upon the use of mini piles, which was going to be possible to install in the confined space within the basement. By combining these different pile types, we were going to have to operate with a reasonably complex 3D FE model to make predictions of the interaction between them. And we were going to end up with a foundation system that essentially acted as a pile draft, principally carrying the load with piles, but carrying a small amount through the new raft that would be used to tie together those foundations underneath the most heavily loaded locations, which would be the cores. We actually found through the back analysis that the single underreams that would be supporting the columns that would be supporting the extended tower could be justified without the need for supplementary piles. And so we ended up with this two-part foundation solution whereby we were utilizing the underream piles for the column positions, and we were utilizing this enhanced pile group underneath the cores, adding to the requirement for us to be making explicit predictions on settlement. And really important within all of this was consideration of sensitivity. So we were considering soft and firm behavior, both in the existing piles and in the proposed piles. And how did this manifest itself through the design process? Well, it was a combination at an early stage of initial hand calculation, analytical approach to give a general sense of what was possible, validating this through very simple idealized FE models, utilizing half space approaches and similar. looking at the individual behavior of both the existing underream piles, and you can see here load settlement curves. This is an example of a soft and firm response. Using that information to calibrate the input that would find its way into our final Plaxis 3D geotechnical model, and then iterating between that ground model, incorporating all of the new piles, the existing piles, the new raft and concrete structures, iterating that with our structural model to converge to a balance between the superstructure loads and those loads within the foundation. That then gave us a series of design outputs, including raft settlements and pile loads. We could use these to check serviceability requirements, both absolute and differential movements between column core positions. But it also allowed us to look at load transfer, this being pile groups. And we can see the agglomeration of piles underneath the cores. Underneath the cores, these being pile groups, we did also have to check that those piles could transfer their load into the ground with an adequate factor of safety, such that our settlement predictions were bounded. We could also use that output to design the new structure from the point of view of reinforcement as part of our ULS design. And so we ended up with a series of underreams being used at a much higher level of utilization than they were previously. So reusing that volume of concrete in the ground in an efficient way, and these pile groups underneath the cores. Where we were utilizing the piles, we actually chose to disconnect them with respect to reinforcement. So there is no physical reinforcement connection between the reused underreams and the raft. This simplified detailing, but it also simplified assessment of shear transfer and other forces that were not necessary for the carrying of the vertical load and would have otherwise driven a critical load case for those piles. Where the piles were not being relied upon, we could backfill with a material that limited the transfer of load between the new raft and the pile, and so limited hard spot. So that was the foundation approach, and once we had that set, we could then also look to the superstructure. And I think one thing that's really important to bear in mind when it comes to reuse projects of this sort is that the design effort is increased. It is, I've often said, like designing 3 buildings in one. We have to assess all of that existing structure. We have to design the new structure, and we also have to design all of the infill structure between new and old. So the design effort is increased, and I think we've got to recognize that. We can achieve impressive things, we can achieve important things with respect to reuse, but the design effort is increased. And we can see the combination of new, the existing, new, and the interfaces within this plan. One of the key decisions when it came to the tower was where to place the cut line. So reinforced concrete structures, it's important to recognize continuity effects. And so we were looking to try to, as far as possible, locate those cut lines at a location where there wasn't significant moment demand. The more moment demand, the more that we had to rely upon adequate lapping of reinforcement. And we can see on the image to the right here, where we did have to rely upon a bending capacity, we ended up coupling between the existing rebar and the proposed. Where it was a lower bending requirement and principally driven by shear, points of contraflexure, we could switch across to a much easier to install short embedment post-drilled bar. Other constraints, we had to make sure there was enough space to get the slip form in, and also to work around some of those existing constraints, like the existing stability system to the bottom of the page here. Also key with respect to our geotechnical design was the prediction of ground movements that that would happen during construction, and we would need to consider that in conjunction with axial shortening. What became apparent is that the new heavy core, in combination with the more heavily loaded columns on the left-hand side of the page here, all of those columns in green are the ones that had new loads being applied from the new floors above, with the intermediate columns being spanned over. And we can see that with the loads on the left-hand side and the right-hand side of this central line of columns, that there may be a concern about the differential movement, settlement, and axial shortening, and the effect that that might have in the horizontal elements. A concern, if you like, about the slabs breaking the back over those columns. And so what did we do? Well, we looked at this through a series of construction stage analyses, working from the original construction of the building through the assumed construction sequence and into the final proposal. And we could then take that to a long-term condition incorporating ground movements. This gave us a way of predicting not only the ground movements, but the axial shortening within the columns, different locations being affected to a different extent, depending upon the amount of load that they were seeing. We could then combine a standard slab model that was on the basis of rigid supports with the imposed movements from our construction stage management analysis that incorporated the ground movements. And by combining those two, we could then look at the internal forces both within the existing and the proposed slabs and check that that rebar demand fell within the rebar provision that we were aware of both from the archive drawings and through the investigations that we did. Interpret that into a series of RC intent and interface details, and we could move forward with confidence. The final thing to close the loop there was to look at any additional punching shear that might be imposed through that movement, both axial shortening and geotech, and we identified a number of locations where we felt that it was prudent to post-install reinforcement using these resin-fixed inclined rebar solutions.
Yeah, so I'll just touch on a little bit about the columns which were strengthened. So a total of over 200 RC columns within the tower in the north podium block were retained for use in the new permanent condition. As David mentioned previously, those columns obviously had to be assessed under the new layout and loading conditions in order to determine whether any strengthening was required. Although the single sort of large diameter underbeam piles that were under existing columns were able to support the new building loads, many of the retained columns, particularly at the upper floors, were taking proportionally much greater loads than their existing design capacity, and therefore needed to be strengthened via jacketing. So two options were proposed, typically around 80 mil thick, high strength concrete jackets were used. However, within the tower floor plates, where the NIA was more of a premium, steel jackets were used in order to minimize any net area loss. These jackets were also left exposed in the final condition, forming a striking sort of interior architectural feature. Yeah, obviously, as we've seen from David's slides, these columns are obviously subject to different axial and bending loads than they've historically been designed for. And therefore, the jackets were designed to effectively carry the necessary proportion of the new total load away from existing RC column in order to avoid them becoming, effectively overstressed. So that was obviously based to a certain degree on the relative stiffness between the existing column and the new jackets, but also took into consideration the benefit of confinement on the existing columns, which was substantial. Sorry, I was going to say from the interaction diagrams on the previous page as well, you can see that the combined capacity of the strengthened columns were in the order of 2 to 3 times that of the existing condition. So there was a huge sort of increase in capacity obtained from this strengthening work. Another consideration with regards to strengthening and can be seen in the interface details between the new and existing structure. Within the podium structure particularly, there was requirements for transfer beams to accommodate step backs within the floor plates above. The magnitude of the reactions from these transfer beams were fairly significant, and whilst the retained columns could technically support the new vertical loads, the connections between the new steel beams and the existing columns would not be feasible as a post-fix detail. So it was therefore necessary in some instances to introduce steel jackets purely for connection purposes in order to ensure adequate transfer of the load into the existing columns. And that's what you can see on the previous image there. I'm now going to run through sort of quickly a selection of site images just to give a bit of a sense of scale and context to some of the diagrams and drawings that we've seen previously. From the images on the screen, on the sort of large one on the left-hand side, you can see the demolition cut lines to the tower, the new slit form core, sort of cantilevering in its temporary condition. The top right, you can see the removal of the facade and the installation of temporary steel cross bracing. And the bottom right, that's the excavation down to the formation level for the new hybrid piled raft that David described.
And we've got a few more images here of the works in the basement. We can see there the 450mm diameter mini piles on the left-hand side up at the top. They've been installed, and we've excavated down to give us the space to install the new pile cap. You see the rebar being fixed on the right-hand side up at the in the middle of the page there. Down on the left, we can see those same mini piles, but now also with the infill over the top of the retained underream piles, and an example of one of the clem rigs that was used to install those mini piles in the confined floor-to-ceiling height within the basement that we found there. And you can see the arrangement on the right-hand side from the plan of the mini piles and the underreams working together as a pile group.
Yeah, and in images here, you can obviously see the installation of the steel jackets, which were formed from two sort of overlapping C-sections, and the final condition in the building where they've been left exposed. And this was also part of the client's aspiration to effectively show an honest building, which internally reflected and highlighted the structural interventions that had been required as part of the extension. And just going in a little bit more detail into the installation of these jackets, we worked with Jay Coffees to develop an installation sequence in order to remove any manual handling, which is obviously necessary given the weight of the steel jackets. From analysing the existing slabs, we were able to give allowable core drilled positions to enable a winch lifting frame to be installed at the floor directly above. The jackets were then basically craned onto canty decks on the side of the floor plate, and small remote controlled mobile cranes, you can see in the top right, which had large magnets, were basically used to maneuver the jackets into place with a subsequent magnet on the end of the winch, which was then used to raise these jackets to support the dead load, and then allow these to be carefully maneuvered into place, and then hit and miss fillet seam welds along the two C's of the jackets. Yeah, again, I'm just going to show a few more images that just want to briefly touch on the construction sequence. And this slide basically highlights, obviously, the extent of retention and the degree of cantilever in that new slip form core. The next slide then shows the sort of final condition where that new core has been stitched into the existing slabs and then tied together with the new steelwork in the extension floors, obviously connected through casting embeds within the slip form. And yeah, so with regards to the sort of overall construction sequence, so the first stage really was to introduce temporary cross bracing to provide sufficient lateral stability. This then obviously allowed for that existing core to be demolished top down. There was a degree of overlap with the installation of the new mini pile foundations, and then the new slip form construction and commenced from bottom up. Due to the speed of the slip form, there was obviously a bit of a lag between the new infill slabs being formed and the level of the core. The core basically approached topping out by the time that the ground floor slab, more or less, had started to be cast. And once the core was topped out, obviously the upper extension floors were sequentially installed until the new frame was complete. This obviously just gives a few images to sort of highlight that process. The first one is the existing building with the external climbing frame for the facade removal. The middle one is showing retained shell, basically, of the tower with the temporary cross bracing in place, and finally, obviously, the completed structure.
And so we're just going to conclude with a few observations on the benefits of retrofit and reuse. I think one of the things that we should highlight about this particular project is that, and this is true of many reuse projects, is that old structure can function within a new building as if it was new. And if we look at HYLO, if we were to walk down the street, just down from where we are here, we wouldn't necessarily understand the extent to which the existing structure has been incorporated. And this is really a good thing, because what it allows us to do, if we compare against these normalized values from government figures, giving us an indication of the relative value of office space depending upon when that office space was completed. If we can incorporate a late 1960s structure into something that presents as a 2020, the data only goes to 2000 that we've obtained here, but if we can get that to present within a building that is a 2020 building, we're going to necessarily increase the rental return, and that makes reuse both the right thing to do, but also an economically viable thing to do. It's part of what it can make it an economically viable thing to do. Another point to make here is really about the density that can be achieved. So we are reusing what is there. We mentioned the additional capacity that we could find in the foundations and the number of additional floors that we could add without having to put any more foundations in the ground when we look to the existing columns. What that allows us to do is it allows us to build taller. It allows us to build denser. And these are maps that look at the public transport access availability from TfL, and we can see that our site sits within 6B, the best area. And so we should maximize the opportunity to utilize public transport. This is showing that more close, and we can see why it's in the best area. It's surrounded by all of these public transport nodes. And within a 10-minute walk, we have Old Street, Barbican, Liverpool Street stations. So there is a premium to height when it comes to structures, but there is also a benefit in achieving density where it is best placed to make use of public transport in particular. And reduces sprawl also. So in terms of overall land demand, it is reducing sprawl. That land could then be used for other purposes. It could be used for greening, for example. And the benefit of all of that comes together into commuting times. And we can see that the draw for this central London location within the yellow area, which is within 60-minute, 1-hour commute, there is a significant area that can be accessed because of the quality of those public transport links. And to finish up with the embodied carbon story, so this is the traditional quality cost program triangle. And we can see now that really this triangle should at least be a square with carbon on one corner. And these axes, we make a decision. We make a decision about where we prioritize the decisions that we make on a project against these requirements, whether we're prioritizing cost, quality, program, carbon. Ideally, we would maximize them all. And hopefully we can see from projects like this that reuse allows us to stretch the priority, increase the priority of carbon without sacrificing, if we do these projects in the right way, without sacrificing quality, cost, and program, because we're reusing what is already there, but we're presenting that reuse within a high quality, appropriate, suitably dense new development. And what does it add up to? Well, it adds up to, in this case, the saving of over 2,500 tons of CO2. It allowed us to achieve LETI 2030 targets on a project, remember, that was essentially designed, the genesis in 2016. And if we want to get a comparison, that might be the equivalent of around 33 cars throughout their life, if we assume 25 years and 15,000 kilometers a year. So it's not a trivial amount of carbon that is being saved. It's a significant amount of carbon that's being saved. If you want to find out anything more about the project, there is a little bit more information on our website. There's a great video with one of our founding directors, Albert, but also Mike is starring in that video. You can go and have a look at that. It gives you a bit of a tour of the building also. You can see more. And we're just going to finish up with a few photos, and I think, Mike, you're just going to give a few observations on these.
Yeah, sure. So I think this, as you said, David, gives a sort of good impression of what you're saying about reusing existing buildings within, something that presents itself as a sort of modern office floor plate. So this first image shows the ground floor reception area. You can probably just about make out in the bottom right and towards the centre the change in size of the column there, and that's because this new ground floor slab has been lowered. So in the existing building, there was a raised stepped access into the ground floor area. That's now been lowered in order to enhance accessibility, also increase the floor to ceiling height within the reception areas. And again, this was part of the sort of client's desire to be honest with the building, to show the sort of elements of structural retention and alteration. This image here just gives you some sort of visual context into how the extension floors look. Obviously, the column spans have effectively been, increased, in some cases doubled. And as we said, secondary spans in steel of about 12 meters is, an efficient use in steel when compared to the existing grid, and that in itself has had a benefit in reducing the extent of strengthening to the columns and therefore carbon cost of that strengthening. It's probably worthwhile just sort of concluding that, obviously, as we've said here, the scheme as a whole has taken what was an inefficient dated office block and made it fit for purpose as a modern workspace, effectively doubling the lettable area, reusing the vast majority of the existing building. And it's hoped that the project as a whole will serve as a bit of a talking point for reuse and hopefully encourage clients to explore refurbishment options rather than defaulting to demolition and rebuild.
And that's the end of our presentation. So thank you very much.
Perfect. So thank you very much, Michael and David, for that. Very complete presentation, and I thank you for delivering such a fantastic project. We have some time for questions, and if you'll allow me to take advantage of my position, I'd like to start with a few questions, if that's okay.
That's fine. We'll switch on our videos here. See our faces. We do exist.
You mentioned it's a 1960s building, so and you tracked down the structural engineer for the project. Was the company still in business, and how good was the information provided?
Yes. So the company was, it was still in existence in a different form. I think the original engineers were incorporated into another consultancy. So we were able to recognise that from the drawings. In terms of the quality of information, I think it was good. In terms of the GAs, there was probably a range of revisions we noticed between floors, so it probably wasn't full and complete as built. And in terms of the detailing drawings, they were good, but it wasn't every single element of all of the building. So it gave us a good background, a good picture. And again, that was sort of part of the importance of these fabric investigations, was to really verify what we had and expand on it.
I think we'd put this in the mid table in terms of the quality of the information. It was a good starting point, but there were certainly gaps. And we can address that through certain design measures as well. It isn't the case that not knowing, not even being able to find that out from an investigation closes the door completely. It just means that we have to think a little bit differently, and often that means sensitivity analysis. It looks at redundancy. What are the alternate load paths? What happens if it isn't quite what we think. It's really engineering at first principles to fill those gaps. Again, more work, but it's worthwhile in the end.
I think what was really impressive, in my opinion, because I've done a few retrofits myself, was that you managed to double almost the height and increase the load significantly with playing around with the columns and mini piles. I think that's very impressive. So,
Yeah.
was there significant over design in the original design, or you're really good engineers, or both?
Well, of course, the latter. No, it was a little of both, but part of working with these existing buildings is finding that, and it's not always just about looking at the drawings. It's also about looking at the history of the building. So what Mike was describing in terms of the provision that was made, particularly in the foundation, wasn't necessarily clear from the drawings otherwise. And we see this on certain projects. It may well have been that foundations were put in the ground at an early stage, the design then changed, and so we get to a point where maybe the design drawings for the superstructure are recording an imposed load that isn't actually consistent with the piles. So it's always worth checking if it's possible, if you've got the information, does it all tie together? I often say, you'll have on an existing building 5 different pieces of information that tell you 5 different things, and part of your job is to figure out which bits work together, which bits corroborate which. So there were certainly some areas that we were able to exploit where there was it's not necessarily an over design, but there was extra capacity from what would be needed for its modern use. The challenge was finding it and then coming up with a scheme that kind of hit those points and maximize the reuse. We kind of generate often heat maps at an early stage. We do this analysis, and to be able to communicate with the wider team, we'll generate some form of diagram that explains, well, we think there's more capacity here and here and here, but this area is limited by this particular component of the structure. That allows us to have a discussion, not just as engineers, but as a wider design team about massing and different alternatives.
Super. Thank you very much. Well, if you will allow me, let's rattle through the questions. We've received quite a lot.
Okay.
So I'll just go through them quickly, first in the same order. So there's a question from Alex or Alexis. Is asking, how do you calculate the additional stress in the sequential construction loading?
So, Mike, do you want to maybe pick up on the columns? I guess that's in relation to things like where you've got an existing stress in an element and we're then adding stress to it. Yeah.
Yeah. So I mean, if we're talking about sort of column strengthening, then obviously there's a degree of locked-in load that you will not get out of the existing columns. Obviously the self weight of the frame is locked in. Where you're adding additional loading onto the floor plates or vertical load, I guess the challenge is to enhance that column, is to ensure that you're not overloading or overstressing it in its new condition. And obviously, part of the jacketing is to remove loading from the column, but the secondary sort of benefit of it is that there's a substantial amount of confinement in those existing columns. And I think there's probably guidance now that David, you can probably touch on it, that with jacketing generally, it almost works as a sort of composite design. So there is a lot of residual benefit that you can gain on the columns.
We took a cautious approach here in that we were generally adding stress, so that we were assuming a certain level of existing stress, and we were adding to that in such a way that the existing material was the limiting factor. But as Mike says, that when these concrete jacketed columns are tested in reality, we actually find that given the confinement effects, given the way that the loads are transferred, they do act more as if they were monolithic. And that gave us then the comfort that our approach was reasonably conservative, but there would be this qualitative backstop, if you like. When it comes to steel strengthening, not relevant on this project, so we're talking about steel frames and so on, the considerations are a little more complex, but with respect to the concrete here, the approach that we took was essentially as we've described.
Perfect, thank you for that. I'll go to the next one by Jess Ritchie. It's a question on the disproportionate collapse. So the question is, did you utilize the concrete jacket solution in order to achieve disproportionate collapse connection requirements between the new and existing structure? And if not, how did you justify that?
So, I mean, the nature of the way that the alterations were made meant that we preserved a significant degree of inherent tying, and so that the principal means with which to address disproportionate collapse, we had that as our first point, that we had the inherent tying. There were a few locations where we'd identified, following an assessment of alternate load path, that the key element approach was required, and in those locations, yep, certainly concrete jacketing and strengthening helps. But principally, the way that we were detailing, you could see some of the continuity that we were able to maintain new to existing. We could maintain inherent tying, check alternate load path as necessary, given the classification of the building, and where we were not satisfied that an alternate load path presented itself, the jacketing then was useful as key element. Yep.
Thank you very much. I've got two questions from Professor Costas. One is about the embodied carbon, and I think you've kind of answered that towards the end. So I will focus on his second question, which reads as, I cannot resist asking the usual last question of the old C-Eng exam. What would you have changed, if anything, in the conceptual design of the building, if it was located in an earthquake-prone city?
Oh, good question. And there was a twist at the end. I think there was enough in the first part of the question. What would you change if you went back? Maybe, I don't know, Mike, is there something just on that first part? What would you change? Put seismic to one side for a second. Is there something that emerged through for our next project?
Yeah, I mean, it's always a tricky one to answer. I mean, there's probably lots of lessons learned in terms of some of the detailing that we could potentially sort of improve. I don't think there's probably not much that sort of on a sort of macro level, but I mean, obviously, could we have retained more of the existing structure? Something that often might be asked. I think the difficulty there is things like trying to retain that existing core and strengthen it and enhance it. I think when we looked at the assessment of that, there was probably more carbon spent actually strengthening the existing core and, you know, almost tacking on existing lift shafts on the side than there was from demolishing and re-slip forming. So there's things like that. I think, you know, that's one area I've always thought about. But I think when you look on the balance of it, the amount of work strengthening it would probably be prohibitive.
I mean, overall, very successful project. But I think the point that you make there about devising new details, that often what we're looking to do with the reuse of buildings means that we have to consider new ways of constructing interfaces and constructing the way that elements are pieced together. And you can always learn from that. And you can always take then experience that you have and experience that is gained from other projects and look to improve them. So that is something that I find very exciting about this type of project. But also what we find really frequently is there's so many drawings, because every interface we have to draw through and make sure that it's designed. And if you're of the right frame of mind, that's a great thing to undertake. But if you're not prepared for it, it can be a surprise. Now, if this was in a seismic zone, I think the original building would have been potentially slightly different to begin with, and the response overall would have focused in on, we talked about fuses earlier, we talked about where to focus to obtain the maximum from the reuse. I think we would have paid a lot more attention to the stability aspects of the building and how to maintain levels of ductility and so on at an early stage, and maybe a little less focus initially on foundations, for example. But it's the whole canvas, the whole building that we started with would probably have been a little different given the age of it and the nature of it if it was in a seismic zone. Yep.
Super. Thank you for that. Very interesting. Yeah, I think the design would be different if seismic was a bigger issue. Just try to go through them quickly. I have a few questions left. A question from Lucas is asking about insurance, building insurance. And the question is, how difficult or easy was it to reuse the foundations from the building insurance points of view?
In this instance, it wasn't a particularly difficult thing to navigate. It is an important question, and it comes up on all projects when it comes to reuse. We took responsibility, as we do, for the design of the foundation, and behind that was a sufficient level of investigation to satisfy ourselves that the design was adequate. Beyond that, it is a discussion between the client and their insurers, and in this instance, they were willing to provide that insurance. It is a case-by-case basis. It is a risk-based assessment. It is never going to be possible to reduce risk to zero. That isn't what engineering is about. It's about reducing it to an acceptable level, and insurance makes up the gap, if you like. And by approaching it as if this were the purchase of an existing building that is then just going to be put into reuse, it isn't that dissimilar when you think of purchasing a building, putting it to use, obtaining insurance, purchasing a building, reusing components of that building in a new design, that with that design being stood by a competent engineer. It isn't too dissimilar, but it's case by case. It does need early engagement. It does need the client to be aware of the discussions that need to be had, but it is possible. It's possible on this project and many of the others that we've looked at, all of the others that we've looked at.
Super. Thank you, David. We have a question, I think, from Nigeria, which is fantastic. It's a question to do with the students and engineering students. So it says, how would you guide structural engineering students to match the structural design theory with practical problems? Because many students struggled, as one of the speakers highlighted, the need to overlap the steel to resist the bending moments at the column beam connection.
Yeah, I think that's a really great point and question, and it comes back to the item that I was mentioning, that really a lot of this is about engineering from first principles, and really working with existing buildings will encourage you to link back to an understanding of how things fail, what the failure modes are, and instead of saying, well, what is the code provision, the question becomes, what am I designing to protect against? What mechanism could this potentially fail by? And for that, you can look all sorts of places, but it's quite rare in actual structures that we see a degree of failure, but often we can learn from that, whether that's earthquake damage, whether it's fire damage, and so on. But there's a lot of tests that are undertaken, and I would encourage people to actually, as far as possible, expose themselves to videos and data from tests that show how things fail, and try to think about how you might extrapolate that to the design situations that you find yourself in. Also, another point, and I think you probably agree with this, Mike, is that it's really beneficial, we find, to be able to be comfortable in drawing and sketching and understanding things to a scale, and looking at the qualitative aspects of a design as much as the quantitative. So those kind of 2 points was what I would say. Anything to add, Mike?
I was just going to say, I think what you touched on with the sort of foundation reuse and the performance-based design is probably something to bring up as well, because we're not necessarily strictly talking about limiting to simple codified factors of safety, etc. Where we're looking at how does the actual system perform with the addition of the mini piles, how does it act as one? So there's, and in those instances we're sort of pushing the foundations beyond their original design. So I think exactly what you said in terms of going back to first principles. I think with a lot of these refurbs, it's a sort of necessary.
And these avenues are open to us, not just within the Eurocode, but in other codes. It isn't that a prescriptive design approach is the only approach. We can take it to a performance-based design, a design from first principles with the appropriate level of testing and appropriate verification. So these things are possible.
Super. Thank you very much. This is an easy one from Tony. It's to do with rebar cover. So asking if there are any issues getting enough rebar cover on the strengthened columns.
Not on the strengthening columns, no. I mean, there was issues with cover in terms of existing slabs in order to meet the fire resistance period. I think generally the columns were fairly good in terms of cover. Definitely for the slabs. I mean, I can't remember exactly off the top of my head what the typical cover was, but it was probably insufficient to give you 6 minutes, let alone 90. So all of the soffits were effectively treated with, I think it was Hynd A90 intermescent coating in order to sort of bridge that gap and enhance the fire resistance. So there's definitely issues with slabs. Columns generally were sufficient.
When you start getting into mid high-rise concrete buildings, 1960s back, it is something to be wary of in that the fire provisions have changed quite significantly, and it does manifest, as you say, Mike, on slabs.
Yeah.
When it comes to the columns, 80 millimeters, we'd come to that through a consideration of tolerances and drawing through the detail to make sure there would be enough cover. Going less than that, you start to run the risk of there being issues. Not that it's not possible, but it's just another indication of kind of drawing through these things. But yeah, it's a good point. Tangentially, that look out for high rise reinforced concrete cover to UK provisions from 1960s backwards.
Thank you very much. I'm just prioritizing some of the questions and focusing on people who didn't ask, because I see a lot of repeat names. So apologies in advance for that. But we have an interesting question from Bokman Choi. I hope I'm pronouncing it properly. It's about BIM and 3D. So the question is, I see a lot of 3D visualizations in the presentation. How did the use of BIM or 3D modeling impact the project?
Mike, do you want to have a... Yeah, so yeah, I guess in terms of BIM, so we obviously model everything in Revit 3D. There was also a cloud point survey that was done by Mace relatively early on after the strip out, which fed into the sort of existing structural model. I'd say it was probably, I mean, obviously, sort of 2016, 2017, it was obviously probably not a different level of sort of BIM than what we're sort of doing on projects, now. For us, it was the benefit of, or I say the benefit for us, it wasn't necessarily that we're collaborating or coordinating with the architects fully in 3D, but we were still modeling fully in Revit. Part of that was for our own benefit in terms of producing details, looking at the interfaces, and also feeding somewhat into the analysis models. But it wasn't, nowadays we are fully coordinating in 3D. Then it was more about for information and sort of.
So, I mean, it certainly brings benefits in terms of being able to communicate, look at things beyond a plan and a section, look at how they relate to each other in a 3D volume. But I think one thing to highlight is that, particularly when working with existing buildings, there is still quite a lot of value in extracting good quality two-dimensional drawings to look at the detail, because at some point we are going to have to figure out whether things do fit together. And it's not that 3D is always superior, it's not that it's necessarily inferior, that they should be combined. So it offers benefits, but I think one thing we would highlight in our response is that we find that there's still real value, particularly when it comes to surveys, in having a good set of 2D drawings to back up the 3D and help interpret it.
Yeah, definitely. Yeah.
Yes, it's always the information. The less information you start with, the more work you need to do later.
Exactly.
Yeah. We have an interesting one. I think this is a quick one for you guys, by Dimitros from Multiplex, talking about rebar and couplings. So he's asking, what type of couplers did you use for the rebar, and what type of rebar did you use? Smooth or twisted, ribbed, etc.
So the existing rebar was square twisted generally,
Yeah.
and so we actually did have to do a bit of work with particular coupler manufacturers to determine an appropriate coupler that had been tested for that type of rebar connection.
Square twisted.
Square twisted, yeah.
Yeah.
But our new rebar was conventional
Yeah.
deformed
Yeah.
rebar. So there are suppliers out there that will provide that type of coupler. Takes a little bit of finding, but it is possible.
Super. Okay, just a general question and a comment to everyone. This talk will be available on YouTube soon. So if you've missed anything, you can follow our YouTube channel for the institution, and you will get that in a few days. And I don't know if you will be sharing the slides, uh, David and Michael, because a lot of people are asking about that as well.
It'll be available through the video.
But I think, yeah, the YouTube
In this
will cover
instance.
that.
Yeah, exactly.
Excellent. So we have a few minutes left. If you're still have the stamina to continue answering the barrage of questions, which
Yep,
I'm
certainly.
prioritizing
We've got
here.
a cup of tea here, so we're okay.
Very good. Very good. So lots of them are kind of repeated. Let's see this one. So we've got an interesting one from the University of Sheffield, a researcher, Charles Gillett, and I'm mispronouncing it for sure. So the question is, do you see a role for benchmark values for use in the initial stages of a vertical extension? So, i.e., to give a definitely no or a maybe yes type of answer. I'm aware of work at the University of Sheffield suggesting potential benchmark value of 10% permissible load increase for Eurocode designed structures and something perhaps closer to 20% for British standards.
It's an interesting point. I think there's benefit in that as a guide, generally, at an early stage. It is really important at an early stage to be able to rapidly respond to different options. I think that's one of the challenges with reuse is that you have to absorb so much information so quickly that it can run the risk of not you can run the risk of not fully opening yourself up to all of the available options. So I think there would definitely be benefit, and we have our own internal metrics against not only comparison of code to code, but also things like material strength gains when it comes to concretes of certain age and so on. There's actually some very good guidance that's produced also by the institution when it comes to appraisal of existing structures. So really useful to have these benchmark benchmark information at an early stage. It isn't going to be a substitute for later detailed analysis, but it can help get up to speed quickly. So yes, we see benefit in it, and we use similar things ourselves.
Super. Thank you very much.
Yeah.
I'm going to ask a general one, which was repeated by multiple people, such as Lucas and Olas Kunami. It's to do with FRP, or the fiber rebar.
Okay. Yep.
So it's a general question that was repeated. So did you consider the fiber reinforcement, and can you tell us about that?
I can probably pick up on that. In this instance, it wasn't considered. FRP rebar, whether that's glass fiber reinforced, whether it's basalt reinforced, and so on, it certainly has advantages, but it also has some disadvantages. For example, its fire resistance and how that relates to cover, creep over time, and its generally low stiffness. It didn't really tick the boxes for this type of project. It made more sense just to proceed with conventional reinforcement. When it comes to fiber reinforcement, without it being polymer bound into a bar, again, it didn't really suit this particular project. I think we're still at a point where we're not comfortable with using it as the only reinforcement in the concrete jacketing. If it were just fiber rather than a bound bar, and so yeah, the rebar really helped. The other downside of fiber reinforced polymer bars is it's not easy to manipulate them on site. If we're talking about bars of a certain diameter, we can manipulate those in steel. We can't really manipulate any of the FRP on site easily. It has to be cut and mechanical anchors. So it didn't really suit, but it is something that we do look at and consider. It can be very light in comparison. Obviously, you're losing a certain amount of stiffness for that lightness. It just didn't really suit here.
Thank you, David. Because of time, we're at the last question now.
Okay.
So I apologize in advance to all the other attendees who've asked very good questions. But I will ask this one from Alexis. And I think it's a good question to tie up this lovely presentation and session. And we thank all of you guys for your input and also our speakers and attendees. So the question, I think, is a simple one, I hope. So it's to do with the existing piles or the existing foundations. And the question is, how did you study the condition of these piles?
So I kind of brushed over this quite quickly when we talked about the investigations. There were a number of locations where we knew we were going to be breaking down. So as part of the second stage, we could actually go in and access the top of those piles, which allowed us to take samples directly from the concrete to look at the extent to which it might have been attacked by aggressive ground. We could also early on take cores vertically through the piles. It's not quite as good as being able to take a horizontal core through. We also were reasonably confident from the point of view of the early soil investigations that we weren't going to encounter a significant risk of aggressive ground conditions. There wasn't any real indication of that in the upper strata, and when it came to the London clay, we weren't in one of those scenarios where there might be pyrites or a risk of sulfates from the oxidization of the pyrites in the clay. So it was a combination of various things that led us to an assessment of risk that we could then validate through essentially physical testing of the piles, focused primarily at the head. But we mentioned also that we did our borehole adjacent to the bell. We could actually take concrete samples. The other benefit of doing that is that we can chisel away concrete at the underream. So it's kind of a low-tech way of determining the depth of the underreams. We're not talking about any cross-hole seismic or anything, but it gives that benefit of it's a physical exposure, and you can actually remove concrete as well.
And you can also measure depending on what depth you hit it at and what the distance is between the two sort of supported boreholes either side, you can actually determine the geometry of the underream to see if it matches the record drawings. I guess there was also low strain integrity testing undertaken to quite a few of the existing piles. So I think that with the ones that, as David was mentioning, with the sort of hybrid pile raft, we had to break down, the top of the piles anyway. So there was physical, testing measurements done of the piles. There was integrity testing. There was some core samples taken to the top where we knew we were cutting them down. So I think all of that gave us, a fairly good degree of certainty in terms of the condition of the piles.